Hello and welcome to today's lesson looking at a change in momentum, which forms part of the forces topic for GCSE Physics. Now in today's lesson we're going to be looking at how momentum can change for an object. So if we are successful and we learn in today's lesson, we should be able to change the momentum and calculate the change for one object, understand and calculate the impact force on an object in the system, and explain why an impact force depends on an impact time. So that's going to look at the following part of the GCSE specification, 4.5.7.3 changes in momentum, which if you'll notice is a separate science only part of the course. So if you do GCSE combined science, this will not be on your examination. Now in collisions and explosions, momentum has to be conserved. This means the total momentum before is the same as the total momentum after for the complete system. Now you can transfer momentum between objects in the system, but the overall momentum of the system will stay constant. Now a name given to a change of momentum for an object is called the impulse. So if an object has an impulse, it has changed its momentum in the system. Now to transfer momentum between objects in a system, to change momentum for an object, there must be a resultant force acting on the objects. Now in a collision we call this the impact force. So the larger the resultant or impact force on an object due to the higher acceleration or deceleration, the faster the change in momentum on the object. Now the faster the change in the momentum or the impulse between objects, the greater the resultant force on the objects. So in a collision, a large resultant force or impact force is bad for you because it can lead to broken bones or worse in a car crash. So it's the aim of any car safety devices to reduce the impact or resultant force to a minimum by ensuring the change in momentum happens as slow as possible. So if the momentum for an object changes, the change in momentum is called the impulse. In a collision, the longer the impact time for an impulse, the less the impact force that's exerted. Now this can be calculated with the following equation. The impact force or the resultant force in newtons is equal to the change in momentum in kilogram meters per second divided by the time taken in seconds. Now you can also write the change in momentum as the final momentum minus the initial momentum. Now it's important to note that you are given this equation in your examination, so you're not expected to memorize it, you're only expected to use it in your examination. Now also remember, we've learned before that momentum is equal to mass times velocity, so we can actually say that the impact force, the resultant force, is equal to the change in mass times velocity over the time taken. Remember that symbol delta or the triangle is the one we use to denote change in mathematical equations. Now it's probably likely that in a collision the mass of the object is not going to change, so we can actually say that the change in mass times velocity is just going to be a change in velocity. So we can write that as mass times by change in velocity divided by time taken. So this is very, very important. This tells us the longer it takes for an object to stop in a collision and for its momentum to change, the less force is required to stop it. So when the impact time is large, the resultant force is small. So if a speeding car crashes, then the time it takes to change its momentum is very small, so the resultant force is huge, which is why it can be very dangerous. So the rate of change of momentum for an object is directly proportional to the impact force exerted on it, which is, we've come across this before because it's another way to express Newton's second law of motion, F equals ma. So let's just think about this in a bit more detail. The longer it takes for an object to stop in a collision and for its momentum to change, the less force is required to stop it. So this is why cars have crumple zones at the front and the back of the vehicles, because they're weak enough to crumple but strong enough to do so very slowly, so it increases the time of the crash, so increases the time to change the momentum, so will decrease the resultant force on the car. Now car passengers have similar protection. Airbags, seat belts, they help increase the time it takes for the passengers to stop and therefore for the change in momentum to occur. So as the time for change in momentum to to occur increases, the resultant force on the people decrease. So let's have a look at this particular equation again. Force is equal to change in momentum over time, which is we call in this particular example the impact force. And remember, we can have a change in momentum because whilst the total momentum of the system will stay constant, the objects inside the system can change between each other. So for example, A could be 10 and B could be 30 before, and A could be 20 and B could be 20 afterwards. So whilst the total momentum was 40 before and 40 afterwards, A has changed from 10 to 20 and B has changed from 30 to 20, so there's been a resultant force acting on both A and B. Now, let's think about this in a bit more detail again, because in many collisions, the change in momentum is the same regardless of the time of a collision. So it's the aim of all collisions involving humans and objects to have a low impact force because it decreases the chance of injury and damage. So you do this by increasing the contact time, because increasing the contact time decreases the impact force experienced by the object. So, and therefore decreasing the contact time will increase the impact force experienced by the object. Now, crumple zones, padding, helmets, sidebars, crash mats, seatbelts all increase the impact time for a collision, so the impact force experienced by an object is reduced. Now, remember, it's important to note that the change of momentum will stay the same in the collision. It's just the time in which the change occurs in. So when the time taken increases, the rate of change of momentum decreases, or the change of momentum per second decreases, which is an important difference you've got to note in your answer. So these ideas are illustrated if you run into a brick wall, because the brick is very rigid, so the time of collision is very low for the change in momentum to occur. This means your impact force is high, which is why it's likely you'll break your nose if you run into a brick wall. But if you run into a sponge wall, the sponge is flexible, so the time of collision is very high for the change in momentum to occur, so the impact force is low. This is why you're not likely to hurt yourself if you run into a sponge wall. So let's just clarify everything again. When two objects collide, they exert equal but opposite forces on each other at the same time. So the change of momentum of one object is equal and opposite to the change in momentum of the other object or vehicle. Because remember, it's the resultant force that causes the change in momentum. So the total momentum of the two objects is the same after the impact as it was before, but they've caused each other to change their momentums because they've exerted a resultant or impact force on each other. So the momentum is conserved, assuming there's no other external forces acting on the objects. So for an example of this in the real world is a bulletproof vest. So the change in momentum on a bullet when it's stopped by a bulletproof vest provides a large impact force on the person, and this would actually crack the ribs of the person wearing the bulletproof vest, which would occur in the real world. So the idea in films where people can be shot whilst wearing a bulletproof vest and be unhurt is not true. A bulletproof vest saves your life, but it doesn't prevent injury because the large change in momentum or impulse provides a large impact force on your body because the time taken for it to occur is very, very short. Now, let's look at an example of how we calculate answers such as this. So a gun is fired at Joe. There's a bullet of mass 0.0040 kilograms moving at 90 meters per second. But fortunately, he is wearing a bulletproof vest, which stops the bullet in 0.00030 seconds. What is the impulse, the change in momentum on the bullet, and the resultant force provided? Well, in these types of questions, you always carry out the same steps. Step 1, work out your initial momentum. So we know momentum is mass times by velocity, so you do the mass of the bullet times by the velocity at which it was moving, and we get 0.36 kilogram meters per second. We then work out the final momentum of the bullet. We know it's going to be 0 because it stopped moving, it's in the vest. Then we do step 3, we work out the change in momentum or the impulse, so it's going to be 0.36 minus 0, so it's 0.36 kilogram meters per second. We can then work out the impact force because you say force is equal to change in momentum over time taken, so we know the change in momentum is 0.36, we know the time taken is 0.00030, so the answer we get is 1,200 newtons. Now the last thing thing we do is, have we put the correct units on? Well, it's a force, so it'll be in newtons. Have we given the correct number of significant figures? Well, it's 2 significant figures in the question, so it's 2 significant figures in the answer, so yes, we have. Another example would be the following. A ball of mass 0.63 kilograms initially at rest was struck by a bat which gave it a velocity of 35 meters per second. The contact time between the ball and bat was 25 milliseconds. What is the impulse on the ball and the impact force produced? Well, step 1, you work out the initial momentum of the ball. So you do mass times velocity. Now initially it's not moving, so its momentum will be 0. You then do step 2, you work out the final momentum of the ball, so you do 0.63 times by the velocity, 35, so we get 22 kilogram meters per second. We can work out the change in momentum by doing the impulse, which is the final minus the initial, or you could do the initial minus the final. It makes no difference because we're working out a change, a difference. So we're doing 22 minus 0, so it's 22 kilogram meters per second. We can then work out the impact force because we do the change in momentum, 22, divided by the time taken, 25 times 10 to the minus 3, because milli means times 10 to the minus 3. So we get our answer out of 880 newtons. Now the last thing we check is, have we put the correct units on? It's a force, so we write newtons down. And have we given it to the correct number of significant figures? Well, the values in the question are given to 2 significant figures each, so our answer should be given to 2 significant figures, which it is 880 newtons. So to summarize, when a force acts on an object that is moving or able to move, a change in momentum occurs. So we can use the equations F equals ma and A equals V minus U over T to give us the equation of F equals M triangle V over T, where M triangle V is the change in momentum, so i.e. the force equals the rate of change of momentum. And you should be able to explain safety features such as airbags, seatbelts, crash mats, cycle helmets and cushion surfaces playground with the reference to the concept of rate of change of momentum, and you should be able to apply the equations relating force, mass, velocity and acceleration to explain how the changes involved are interrelated. So if you've been successful and you've learned in today's lesson, you should now be able to calculate the change in momentum for an object. Then you should be able to understand and calculate the impact force on an object in the system, and finally you should be able to explain why an impact force depends on the impact time. I hope you've enjoyed today's lesson looking at the change in momentum for objects in a system, which is part of the GCSE Forces topic for AQA Physics. Thank you very much and have a lovely day.